So let me now briefly recap some things that you should already know from school, but that are useful nevertheless to have a quick chat about again. So let's call this part of the lecture elements of a microscope. And so before I go into that, let me just recap some simple geometric optics. So you can see again how we think about forming images with lenses and so on in simple ways. So if I have a object and it has a certain size, let's call that size y0 or yo for the object, and I have a lens, an objective lens, let's say, like this, then I can find out where the image is using just geometric optics as follows. So essentially what you do is you draw three rays. The first one is called a parallel ray, and this parallel ray is focused exactly one focal, is not focused, so it passes through the focal plane at the other side of this convex lens here. So this is a convex lens that we're looking at. So if this is this distance here, we call f. This is the focal distance, and then the equivalent focal distance on the back. So we draw the equivalent point on the back of this plane, and then the light from this ray we can represent with a ray that goes through the back focal plane. So this is the parallel ray, it's called. And the next ray we can draw is the so-called central ray. So let me just try and do that. So here is the central ray, and where these two cross, you get the image formed from that object. So now we have the image. So the extent, the lateral extent, is now yi when it was yo for the object. So we call this the object, and we call this the image plane here. And so this was the, let's call this the central ray, let's call this the parallel ray, and this is called the central ray. So the central ray passes through the center of the lens undeflected. It just goes straight through. Equally, we can draw a ray that goes through this, through the front focal plane, and that will come back parallel, and in fact it meets the other rays exactly at that same plane. So this is called the focal ray. So with that you can see what you get is an image. This image here is called a real and inverted image because it is inverted. So if this is a positive distance, y0, then this becomes a negative distance, yi. So the image is inverted. So you start off with something like this, then the image will be inverted and magnified or demagnified, whatever it is. So if I now call this distance here, if I call this distance here, between the object and the objective lens, let's call that SO, and let's call this distance here SI. Then from Newton's lens formula, you might remember, so let me just draw in again, that was F as well. That's called the back focal plane. That's the front focal plane of the lens. So this might be the objective here. And then you get a real image formed at this position. So that you find from Newton that 1 over f is equal to 1 over SO plus 1 over SI. From that formula, you can work out where the position SI is of the image. If you know what SO is, you could measure that and find out what SI is. If you know what F is for the lens, like this. Okay, and the magnification is obviously the transverse magnification now, as this is called. So one way we said the magnifying power was the ratio of angles of aided and unaided eye that the sample subtends. And this here, this definition, is just the extent yi divided by yo. And there are going to be a few simple questions in the question sheets that that you will get just to practice a few of those things. And you can do the same thing also for concave lenses. So this image here would be a real image. By real, we mean if you put a screen there at this position SI, then you would really see a screen you would really see an image on that screen, very much like what's happening with this projector here. So this distance here from this sheet of paper to the lens is SO, and then from here to wherever the screen would be that you actually see would be SI, right, in this imaging system. So that's exactly what goes on. You can do the same thing, and please look that up again, how you would do that for a concave lens, right? So this is a convex lens, and for the concave example, you do not get a real image. You cannot project it in the same fashion. But you'll play with that a little bit. But now let's go and discuss what a microscope is. You remember Newton's, Hooke's compound microscope. And you will be surprised what the model is that we use for this. It's very simple. So if I have let's grab another sheet of paper. If we have an object, again, it looks like that, and then we have an objective lens, like that, and then let's draw this in. So that here is f0. Then we go to the back focal plane, again f0 for the objective. And then there is a tube lens. Let's say, I've drawn this badly, please forgive, but you get the picture, right? So this is called the objective, as we said. This is called the tube lens, like that. And now this is the front focal plane, ft of the tube lens, and then you have the back focal plane, ft of the tube lens. And so this is where your image would be formed. You would get your image somewhere down here. Okay, exactly in this thing. Now there's a couple of things to note. This is it. This is all we will be describing in this course, this lens system. It looks trivial. It's not quite that trivial, but actually everything can be reduced to this simple compound picture. An objective lens and a tube lens, and you get a real image. You might put a camera there, and that's where you get your thing. You get the magnification from the objective, you get a magnification from the tube lens, and then together you get the overall magnification, whatever it might be. It might be 300 or 400 for a good microscope, or even higher if you get the system right. And so what we want is the best possible resolution, the best possible contrast of the image that we get with a given system. Now, one thing that you do in the modern microscope is you put the sample exactly one focal distance away of the objective. That's exactly where you place it. Now, what does that mean for the light? That means because we now so what this means, if I am exactly one focal distance away, then all the light that comes out afterwards is parallel. So any light that goes from here through this objective lens will end up being parallel, if you think about this. So anything that you draw from this thing will be essentially a parallel ray of light coming out. And I've drawn this actually badly. This is wrong what I've done. I should have started like this, and then that is parallel, and then this central ray goes undeflected. You know, as I said before, the central ray is always undeflected. So in fact, if you think about this, what will happen is light from that point will go down all at that angle. It will still be parallel, right? You work that out using the lens formula and the simple tools that I gave you up here, where all the points, the light point, you know, that the light from the sample here will end up. But essentially, all the light here is parallel. It turns out in this configurations, and of course, then if this ends up on the tube lens here, then then the image will be formed because parallel light is coming onto this lens. It will form exactly a focal distance away, the tube lens focal distance away from the tube lens. This imaging system is called a 4F imaging system. It has several advantages. It gives you the best quality, best imaging quality possible. And it has another nice feature, which is that this space between these two things, because all the light in between is parallel, it's actually not so critical what the exact distance between these two lenses are. You can actually make it slightly larger. You still get exactly one tube lens away, one tube focal length away, the image position, right? So that allows you to change this distance without actually changing the magnification of the sample. The magnification is simply given by the ratio of the focal length ft over f naught. I'll write that down in a minute. But this space here in between, and this is really important in this 4F imaging system, is called the infinity space. And this makes the system this makes the system very flexible, because you can easily change objectives if you want. So if one objective needs to be a little closer to the sample, then you just shift the objective that you want closer to it. You can easily change the objectives by essentially just placing the objective lens in the correct position, so that you don't have to move the sample. So you know when you have these lens turrets, by having this 4F imaging system, you can just flick the turret and the sample will be in focus again and give you an image. The magnification here, MT, and I'll leave that again to you as an exercise, is given by FT over F naught, or F objective, and that is given, again, you can also write that's magnification of the objective times the magnification of the tube lens. So this would be, so it's related to these angles again. The magnifying power, you can work that out too in what you want to do. I will want now to switch back to the slides in what I do, because, well, hang on, before I do that, I'm sorry, before I go back to the slides, let me just do one more quick thing and define two more microscopes for you on paper, because it's actually easier to draw it. You learn better by doing this. So the first one is the so-called inverted microscope. And this is the microscope that is preferred by biologists, biological samples. So the way that this works is that, let's suppose I have a light source, a source here, the light source, and then I have a condenser lens. I didn't draw a condenser up here. You would have a condenser here to illuminate the sample, and then you get these rays of light coming out, so there would be a condenser lens. But actually the important part is objective and tube lens for most of what we do. But in the inverted microscope, if I now draw the source explicitly, and I have this condenser lens, so I throw, this is called a condenser, like in Hooke's compound microscope. Then I will have the sample here. The sample may be in a little chamber with a little transparent glass bottom, a little glass piece down there, and then maybe you have a cell in there with a nucleus or whatever, and so the cell may be happily sitting in some water so it doesn't die, and with culture medium, and that's why biologists like this microscope, because you can contain samples in these dishes without the cells being unhappy. You can just replace the sample in and out. And so the way that this works is you throw the excitation light onto this. So you have light coming from the source. You flood it with light, parallel light coming out, right? And then you have your objective down there. You look from underneath. Then you have your tube lens. It's exactly this configuration here. And so let's suppose I have this point here I'm looking at. So this point will form an image exactly one tube lens focal distance on the image plane. So here you may have the camera, the CCD chip. And that's called an inverted microscope. So we have tube, objective, this is a sample chamber, and this here is a cover slip, it's called. So it is a transparent optical piece of glass. All right, and so this is where the image is. And that's okay. So the fluorescence microscope is exactly the same thing. It's the same idea, but so this might be a bright field microscope, as we've just seen. So light comes on, the light is refracted by the cell. This is what we see. We get the low contrast bright field image. So this is called a bright field image, bright field microscope, right? But then I can also build a so-called fluorescence microscope. Let me just try and find a piece of paper. So the other important microscope is, and it usually is an inverted microscope, often is, doesn't have to be, it can also be an upright microscope. So the alternative, the alternative is the upright microscope. So in the upright microscope, you really just switch the tube lens and the objective lens the other way around. So you form the image on top and you illuminate from the bottom, and that actually so you flood the light differently, and that makes a difference, right? And that can be used for other samples that may not be transparent. So you look from the top down. Okay, so the fluorescence microscope. It looks like this. I have my sample. If I make it an inverted microscope again, like this, here's my cell, the light, and then what I have is I excite this sample like so. So I have an excitation source, a lamp. The lamp throws light onto the sample. I bounce it off a so-called dichroic mirror. I have my condenser lens here. This is the condenser. So the light is focused. I'm not drawing this, with proper focusing and stuff like that. It's not important. But then I have here what is called an excitation filter. And then this is a dichroic beam splitter. beam splitter, this thing here. It reflects the excitation light up onto the sample, the blue light, and then the red shifted fluorescence light, it will actually be transmitted through that dichroic filter. So that rejects the excitation light that may be scattered off the sample to come back and reduce contrast. And you can further increase the contrast by putting what's called an emission filter in here. And that passes the fluorescence signal. So the fluorescence signal, so this is the fluorescence signal from the sample, and it passes through the tube lens. So here will be the tube lens, and it and then it forms the image one. It forms the image one tube focal length distance away from the tube lens here. So that's the images here. So that's where you place the camera chip. There's one very important thing I've forgotten, which is the objective. The objective is here. So the condenser will, so in this example, the condenser produces light that is then focused with the objective onto the sample. So the objective serves both as another condenser, if you so will. It will flood the light with the excitation. It will put the excitation light onto the sample and collect the redshifted emission light. But that's now passed through this beam splitter here because it will pass the fluorescence color but not the excitation color. You can further clean up the signal by having this emission filter, and then you get your image that way. And that gives you very high contrast images. And that really is all to it. I mean, so for most of the microscopes, we now just need to know how they work. But before I do that, I'll go back to now my presentation.